Guys, welcome along to the our ModSim webinar today. As you can see, I'm not in the office, neither is Andy. We're both out and about with customers. So yeah, obviously going to give you a little bit of background about myself. I'm relatively new to Technia, been here for a couple of months now. My background is in engineering design, specifically used in SOLIDWORKS for the last, 10, 15 years. And before that, I was working with Siemens, looking after Solid Edge and NX at the time. Then I moved into with the SolidWorks channel, getting very involved, with a lot of customers, going through the same pain points that we're going to talk about today. So yeah, like I say, welcome along. We'll go through it and hope it's beneficial for you and, touches some nerves with you and answer some questions if possible.
So, I'm Andrew Steele. I'm one of the territory sales guys here at Technia. Very similar background to Barry, that we went to the same university and both qualified as designers, product designers. Been using CAD since just before turn of the century, and yeah, it's always been a big passion. So I've lived that life of chasing QA managers and design managers around the office, trying to get drawings signed, and also the pains of trying to get a product from an initial sketch on a piece of paper through to actually being manufactured and then working in the real world. So you've joined us here today to talk about ModSim and how it can benefit your design processes. So as a kind of a warm-up to that, ModSim's obviously not a real word. So we try to think, how could we explain the concept of ModSim in the most simple terms possible? And so I decided to use the analogy of a chef's kitchen and a taste test. So we've got a little video here. It's only a couple of minutes long. We'll watch that, and hopefully it'll give you just a sense of what it is we're talking about when we talk about ModSim. So bear with me, let me press some buttons.
Have you ever wondered what engineers can learn from a chef's kitchen? Probably not, but we think you'll be surprised by the similarities. A good chef makes sure that every meal is made to exacting standards. Each plate must delight the customer, be repeatable, deliverable on a tight schedule, and generate profit for the restaurant. As ingredients are added, chefs repeatedly use the taste test, a quick but vital check to ensure confidence in their creation. Once ready, the meal is plated for the head chef to pass for service. As engineers, we have a lot of similar requirements. It's got to be right first time, it's got to delight the customer, be innovative and be sustainable, and finally deliver a profit. But what's the engineering equivalent of the taste test? Well, we all got taught the familiar engineering design process at school. It's typically made up of 7 or 8 steps. We ask questions, do research, imagine solutions and plan. We create what we've imagined, and then we test it. And then we try to improve what we've got. We've placed our plate on the pass without tasting it, and we hope it'll be approved. So we're assuming it looks right, it is right? Each of these steps requires the use of game knowledge, usually held in the heads of the most experienced designers in the room. And with limited collaboration between each design phase, we often over-engineer products. Failing at the test stage can be expensive, and nobody wants the person that got it wrong. So how can we solve that problem? Well, this is where ModSim comes in. Mod from modeling and sim from simulation. It's a data-driven, collaborative and concurrent approach to product development. In other words, it's the engineer's equivalent of the taste test. ModSim keeps your existing design process intact, but wraps it in a continual testing process. It gives us a much better understanding of the problems we're going to solve, enabling our solution to exceed defined requirements. It rapidly increases confidence in our solution throughout the development cycle, and that final test becomes confirmation rather than a question. So, looking back, we're likely to find that if it looked right, it was probably over-engineered. So, how can Technia help you make the most of a multi-team philosophy? We can train you in the process and show you how to implement it. We can provide engineering services so you can outsource the testing to us. We can provide software and training so that you can do it yourselves. We can provide engineering consultancy, or we can handle the entire design process for you. Get in touch with Technia today to discuss how ModSim can deliver business benefits to your organization.
So there
I
you
love-
go.
I do love that. Again, though, Andy, that it's not just engineering. If you think of painters and decorators, they never put a tester pot on the wall without speaking to your wife and saying, "Is it right?" Testing it, check with me or my other half before you even go to the next step. So that applies, I suppose, to multiple different scenarios.
And yeah, you're absolutely right, Barry. And there's so many other scenarios, anything which is really a creative industry where we could care that what's going to be coming out at the end is right. If the issue has always been with engineering, the testing was expensive. It took a long time to do. So we put it off as far as we could until the last minute. But like I was said in the video, in order to get there and know that it's going to pass, we'd over-engineer the product to make sure it did. And the whole, if it looks right, it is right. I've heard that so many times when I've been in a design office. So if I flick over now to the next slide, Barry, which is you, I think, going through.
Yeah. So obviously, guys, this is the oh, someone's trying to get in.
I think Jen will do that for you, Barry.
Okay, so this is the first of 3 seminars we're going to go through. Again, touching on the process that Andy's defined in the video about looking at testing early to make sure we hit the market with the right product the first time for the right price. Obviously, cost is a huge factor nowadays. So yeah, the first seminar is going to be looking at the big heavy machinery. Anybody who's been with SOLIDWORKS for as long as me and Andy have, this demo set's been used for an awful long time. The guys called Resumen, they're over in Peru. They've given us the data set, which you can use. Again, for us, it's a perfect example, of how they're using this whole ModSim approach to the way in which they conduct the business. Test it early, make sure that any variance that they have in production is going to be fit for purpose, so that when they press button before they even commit to them, they know it's right. But again, like for me, Andy, I think this is a perfect example of going through the process and trying to explain it as simple as possible. Yeah,
exactly. And the second one.
The second one, we're going to be looking at this a dolly from a train here. In particular, looking at the bushing for the suspension in there, looking at some non-linear analysis in there, and the third one's going to be looking at this water jet cutter. So this thing goes through high pressure. So as you can imagine, the cutting nozzle at the end there goes through all sorts of forces in its lifespan, either from the movement of the bed or from the actual water being pushed through the head there. Again, trying to making sure it's reliable and again safe for operation. But again, by all means, make sure you get registered. Come along and join us, because they're going to be very informative, to the point, I think, but hopefully relate to the same process that we've felt the pain from.
Yeah, definitely. And as we go through, the simulations do get progressively more complex. So especially as soon as we move into the next one, for the rubber bushing, there really is quite a leap forward there. But let's start with some linear static on this one. So what are we using to do all of this? We're using the 3D Experience Works platform. Now, it's a whole host of applications and roles within the Dassault 3D experience. And it's an integrated system, and all of those bullet points that you've got there, it's designer centric, it's comprehensive. Whatever industry you're in, we're going to have a solution that can be tailored to your requirements, be that industrial equipment, be that in the automobile or aerospace, be that in life sciences or medical devices. The 3D Experience platform really has got a solution that can
I think one of the other things, Andy, is that, you know, you've got the bottom there, collaborative. You know, how many times have you been asked, can you just modify that? Can you make a change? Can you give me a drawing of this part here? If you give the people in your business access to the information, the right information at their fingertips, that is huge time saving for you guys in industry. Create a drone, do a test, it's all there for them.
And on the platform, it's on the cloud, it's stored securely. So be someone in Peru that we mentioned, or the States, or in the UK or Europe, all of that data is easily accessible. You've got no IT costs that you're going to have to invest in. The platform just runs and it updates itself automatically every month or two. I don't quite remember what the schedule is, but you know you're always going to be working with the most up-to-date software. It's a fantastic leap forward. I've been in SolidWorks for 20 years now, and I saw, and you saw, Barry, the way that SolidWorks revolutionized the design department. And there was other products
from a pencil and a ruler.
Yeah, well, exactly, from a 2D CAD package. But the 3D Experience platform takes that revolution from just the design office and puts it throughout the entire organization, and allows the entire organization to be part of the decision-making process. And it's all that comes back to ModSim, the collaborative decision-making processes sooner that help you innovate and be that step ahead of everybody else in the market.
I think obviously the pandemic as well, Andy, you know, everybody's wanting more for less from the business. You hear that again. How can we get more for less?
Exactly.
So this is
we're all working from home, and the platform is the ideal thing that ties us all together and allows us to feel like we're still working in the same office. So today, what we're going to be using specifically within that 3D Experience platform, we're going to be talking about SolidWorks, and that's what we're going to use to do all of our modeling. And then we're going to be talking about how we collaborate with SIMULIA, the simulation package on the platform. So some great interaction between that software we're going to see today. But just because we're talking about SolidWorks here doesn't mean it's the only package that can do this. CATIA, I know quite a few of you out there are good well using CATIA. The exact same functionality that SolidWorks has got to talk to SIMULIA is in CATIA as well. So if you just, wherever we use the word SolidWorks, feel free to interchange that with CATIA, because you're getting the same functionality. So Barry touched earlier on this, but this is what we're going to be working with.
So like I say, guys, there may be guys here who've seen this demo set. I've used it for years in SolidWorks, you know, promoting large machinery stuff with a customer. But again, you know, the principle that these guys are going through, they've gone from having something like 120, from something having 3 different variants every year up to 120 something every year, just by being able to test early, validate it, make sure it's, you know, it's fit for function before they even commit to tooling. So these guys, their drivers, keep the costs down, make sure that we stay market leader and beat the competition. And again, we're very fortunate in the fact that we've got the data set, and they're very keen to promote, you know, SolidWorks and the platform. So yeah, like I say, it's going to be going through all of that and testing it, and again go through the whole ModSim process. Yeah.
Okay. So the part that we're going to specifically look at on this here is this part just. Can you see my cursor there, Barry? Is it showing?
Yeah,
So
the boom
we're
arm.
looking at this boom arm assembly just here, Could we run an assembly on the entire thing? Yeah, we could, but we're only really interested in the stresses that are happening in this part here. So let's zoom in. So you can see here that we've got the struts and the arm. Oops, there we go. So here's the struts and here's the beam. And this is a big lump of machinery, which is probably worth mentioning because it'll be coming up in future slides. So this CAD has been built at the moment on my desktop using SolidWorks, using a normal seat of SolidWorks, and it's saved locally on my machine. So I'm the only one who's got access to it. So I now want to start collaborating with the team. This is just an idea that I've come up with, and I want to make sure that it's going to really meet the criteria that we think we know. So what's the first step that we need to do? We need to get this data into a state where everybody can use it. And we do that by pushing it up to the 3D Experience platform, which is what you can see there in the little monitor picture. So let's walk you through how we actually get this up onto the platform. So first, we need to log in. And this is how we activate SolidWorks. It's different to what we used to. We used to go and start, but with the platform, we log into the 3D Experience. This registers us into the data center, and then we start SolidWorks directly there. Now, we know that our session is created and we're up and running. The next step, we find the data that we've been modeling on our computer. Open it up, so we find the boom assembly there. And then you see on the right-hand side that we've got a new panel that we wouldn't traditionally have in legacy SolidWorks, for the sake of saying it. And this is showing us what we can do with regards to the platform. So now what we've done is we've said, convert these files and push them up to the 3D Experience platform. Takes a few seconds to do it, but up it goes. And now it's been converted into the relevant format on the platform.
So Andy, is that just gone up there, pushing to a revision stage? Yeah.
So yeah, if I just bounce it back a little bit, there we go. So yeah, all of these files have been pushed up into the platform as revision A1, and all of the so now that is there as controlled data on the platform. And now on the platform, I can do a search for ASM Boom, which now allows me to open directly that CAD data on the cloud. Now, I don't have to be a SolidWorks user to do this. This is just within some of the roles that are on the platform that I can go in and interrogate models. This allows anybody within the project who's been given the privileges to do it to see what we're working on and see how things are developing and give their input towards it. So now my data's on the cloud. Barry can access it. So now it's Barry's turn to start, because Barry's going to play the simulation guy. I'm the designer, but let's move you on to the next slide. So,
right. So in simulation modeling, I'll walk you through how we're going to do some finite element modeling and mesh the connections, get it all in there. We're going to create some explicit dynamic steps, contacts, loads, and look at the outputs. Yeah. In the results, we want to see how we can create customized history plots, engineering rules, and checks, and check all the information. So we're going to apply the material, run the mesh, apply any bolts, the connectors into there, and then look at the steps coming at the back end of that. Yeah. And then make modifications that I'll then pass to Andy to then, update the SolidWorks geometry to then make sure that it meets the criteria that we're trying to achieve within there, and it performs as it should do before we even commit to tooling.
Okay. So now on to the good stuff. You ready?
They are indeed, yeah. Yeah, so the first thing, if you guys are similar to SolidWorks, I'm going to apply the material. You may have applied it in the 3D geometry itself, but from here on the platform, I'm going to make sure that I'm assigning all the metal to be this A36 plate, and assign that to all the parts that within the assembly. The next step, we're going to create the mesh rule, which is going to run through the whole assembly based on some parameters that we're looking for, and then apply a tetrahedral mesh to that particular geometry. If you think of this mesh rule, it's kind of like you creating a template that can be used by, again, by yourself or other people. So it's kind of all bundled up into the data on the cloud within there. Yeah, so I've applied it to all the parts. So then here I can either go step by step, but I'm just creating a user-defined one and apply that to all, so you can see it's working through and assigning that to the geometry within there.
And
Apply that to all parts.
Green traffic lights. I like green traffic lights. Showing us we've got
it's now been, it's good, all gone green. Tells me that's all good. That's all applied. The mesh rule's now there. And now, as you can see, we've got some bits of information. But the next thing I want to do in here is go in and start applying. You can see the mesh rules now run through there. Everything's going meshed on there, which again, one of the benefits here is, you know, if we make changes, it recognizes the geometry. As you can see here, we're going to lift the boom arm up very quickly to then modify that and apply that same mesh to the new assembly in the new position. So very quickly that updates that whole geometry within there.
So yeah, and I think that's worth drawing attention to, because it's incredibly powerful what we saw there happen in a matter of seconds. So Barry's got access to the data that I've created in CAD. It's now on the platform and he's working with it. He's started doing a simulation and it's all meshed up, ready. But then modifications happen to that SOLIDWORKS data. Now, in the olden days, that potentially meant that we were going to have to resave the files out from SOLIDWORKS into whatever file format our simulation package required, and then potentially Barry was going to have to remesh it. But there,
again, yeah,
that data has moved through, and we're working on the same data, which just brings all of that collaboration through. So yeah, I want to just stress that, because I think it's skirted over slightly in that step.
Mm-hmm. Yeah, so the next thing here, we're going to create the virtual bolts. Again, you could model them all in SOLIDWORKS, but as you guys know, the more information you put in the geometry, it's going to be hugely kind of labor intensive on the graphics card of your PC. But from here, I can go in, understand there's a pattern there, and I can apply the bolts to this. And again, the good thing there, massively saving time. It will then tell the simulation when I run that these are, you know, the right type of bolts, doing the right bit of information in there, so that, you know, they're going to perform as it should be. So we can see that they're now all in there based upon the pattern. And we're going to hit apply on that to make sure that yes, them bolts are good to go. And away.
So Barry, on that one, what if this was a much bigger plate of steel and it had 100 holes through it for nuts and bolts? Have I just applied one, and it could have been 100 that I've done?
And it could have been loads. Yeah, so a huge time saver for you with that one. Rather than having to go into SOLIDWORKS in the toolbox and go insert bolt, then insert a washer, insert a nut. It does it all for you. It's all there, ready to go. And the key thing there, once they're in there, that's then pushed to the simulation side. So the next thing, obviously, you've missed off putting in a gas strut here. It doesn't really matter. Similar to the bolt, I can apply what we call a translator connector. So I can define, obviously, there's going to be a gas strut goes from up the middle of the boom arm there to the bracket down here on the main sort of body assembly. So we assign the circles on there, and it picks up that's going to be, you know, a gas strut in there, even down to the dampening of that as well. So we can define that, you know, the loading, is it going to soften as it bounces down, all the rest of it, and that will apply. So when you apply load to that particular bit of geometry, one thing that, you know, the guys that they're looking to see is fatigue, you know, the movement of that, you know, the arm. there could be a machine on there, Andy, that's riveting holes for all we know. So they need to work out, the right stresses are applied to this, and it's going to perform as it should do. Yeah, so I've kind of mentioned, the machine going on the end. I'm going to create a coupling. So from the end plate, I can see going to see where that connector is going to be. So if we take the kind of the center point of the mass at the end there, we know that roughly the new machine is going to weigh just under a ton in weight on there. So we can, from that end plate there, we know there's going to be a ton applied to that based upon gravity and the downward motion applied to there. And it'll work. Again, you may want to put in a number of different steps in there, looking at, whether you've got kind of movement, if it's going to be a drill or, in another direction. So we can build that, that step up within there.
Okay, wait for the next one.
So we're now in the cloud. We're going to run some simulation in here. And we'll look for the boom from the name that we gave it before. So we're going to load the information into there. Do a non-linear, create a static step on here. Like I say, we could build up a number of different cases of different functions in here, whether it is if it's moving, look at the fatigue life within there. So we define all the parameters that we're going to do within there. So the next step here, obviously the boom arm moves in and out on its length there. So we need to make sure, check for any contact. So we can then run that study on here to see if there's any areas where there may be a bit of interference, and define it as a potential connected area on there.
So effectively, you've said, yeah, these things move, but for this, we're not really interested. Just effectively assume that they're not going anywhere.
Yeah.
Okay. All right. Yeah, I see that there.
Yeah, so you can see, and it'll highlight the areas where they are. Surfaces may be moving against one another in there. Yeah. Yeah, you go get little dots that pop onto there to show you where they are. So you can see all the areas that can apply to that. So we create the restraints from here. So we know that the boom arm is going to be fixed from that back plate to the machine. So we can define that and apply that in here. Yeah.
Okay.
And then start running the analysis on here. So I can see all the forces that are going to be applied to the coupling, to the where the arm is, the machine at the end of the arm there. You can see
Okay,
that
one's going straight down.
Yeah, but there may be one applied straight down the boom arm itself.
Okay.
And if you've got any moving parts that's going to oscillate, or like a drill, if you like, we may want to define that. So we're looking at the fatigue life of this particular part within there as well. Yeah.
Okay. So far now we've applied one load which is going straight down,
and one down the arm.
Going down the arm. So why have we done that? Is that we've applied it going down the arm?
Again, we know that the machine arm weighs just about a ton, so there's going to be a force applying to the arm there. That's one study. But in addition to that, if it's a drill, it may be pushing against a wall of a quarry. There's going to be forcing that down the arm. Again, is it going to have any movement on there for the fatigue on that one? Looking at vibration, is it going to fail? Yeah. So we can literally build up the analysis and compile that study together. Yeah.
Okay. Right.
Yeah.
That's what you're doing.
Life cycle study in it. So look at the fatigue that's going to be applied to that. Let that run. So we can see in here, so we can run the model and run the simulation checks on here. So it's going to go off and do all of that based upon the parameters that we've put in there. It's understood the material, any fixings that are in there. That now has been, run through. Either it's going to be on your local machine, or we can do that on the cloud. Sorry. So again, we can look at different sort of settings to work with you guys on that one.
Yeah. So that can go all the way up to 144 cores.
Yeah.
It doesn't necessarily mean that 144 cores is quicker than 4, or 32, I think we picked on that one.
Yeah.
If you want some advice on how many cores you need to run your simulation, come and speak to us. And me and Barry probably aren't necessarily the best ones to answer that question for you, but we have a team of very, very clever simulation experts at Technia who will be able to give you a good idea of how many cores that you need to be able to run the simulations you want. So there you go.
Yeah, so we can see that based upon some of the analysis on here, we can look at the plots, we can probe the model at any point within there and see where the stresses are. Look at, investigate that to understand is that there's a bit of movement based upon the load on there. Look at the XY plots and look at the von Mises stresses that have been asserted to this particular machine. So we can I can start making judgments or advice to Andy to then pass that back to him to say, can you consider, increasing the wall thickness in this particular area because it's going to come under quite a bit of stress, and the fact that certain areas based upon the fatigue might be kind of under a lot of stress in there. So we can analyze the data and get that fed back to him very quickly to make those changes. We can look at sensors being applied to there, so we can get information from here to get feedback from the system to say how well this has performed in there.
I guess that'll give us something to be able to track it by in the future.
Yeah, so in here we can see it's failed. So we're trying to go fatigue life of 7, which is nowhere near where we need it to be. So then it's failed on the stress and the fatigue in there. We can look at the plots.
I'm not playing the same video again there. I am, aren't I?
You are, yeah.
Okay, so yeah, so this is where you want to be.
That's where I need to be, yeah. Yeah, so from here we can see that the fatigue life of 7 it's not where we need to be. You can see the hole we're looking for 5.86, it's achieved 7. So we know that in that area, you what?
Other way around, we've achieved 5.6.
Yeah, and required 7. So my glasses Andy falling off my head. Yeah, so we need to make some modifications. So I can give this information back to Andy and say, before we commit to tooling and spending any money, can you modify that box section there to increase that wall thickness to try and make it a bit stronger in here? Gut feeling being part of this, but based upon the ModSim, can I get this back to Andy before we even commit any money to making the machine that fails? He can then modify that, get the changes needed as required on there. So hopefully it won't fail when we run this, because those tests have now been stored on the cloud. When we make the modifications, it can just fly through and seamlessly get to the results significantly faster.
Okay, so me and Barry have had a meeting, and he's jotted me a little message just saying, right, Andy, I think we need to change this. So he's come back and he said, oh, that failed the criteria that we needed to do. And he suggested to me that we need to change the thickness. So I'm now going to go away and do that. But also now, because Barry's done a lot of that work creating that simulation, I'm not a sim expert. And we've now got access to the assistant panel. Now, this is a really great way of people who aren't experts using a wizard to start being able to do some lower level simulation themselves. And we'll touch on that in a second. So Barry's come back to me and said, your wall thickness is 8 millimeters. I suggest going up to 1/2 inch, 12.7 millimeters. So I'm now going to go back into SolidWorks and open up the same model that Barry has run that simulation on. I'm opening up that part of the boom. And then I'm going to access the feature tree, go into the sketch, which defines that boom arm. Now you can see here that I've got an 8 millimeters at the top, but rather than just changing that dimension, I'm going to start assigning some parameters to it, some variable names. And I've done that to the host of them there. We flicked through it really quickly. But now those dimensions are exposed to anybody else who needs to be able to get access to them. And then we push this back up into the platform. Now you'll notice, there we go, we save that, goes up to Barry, and now I'm going to run my simplistic test. So it's already set up, the materials have already been assigned. I just want to test this one part though. So it walks me through, specify the mesh, it automatically puts it on, create the bonded contacts again, and it's finding the pairs there. We apply the restraints, again, much nice and stepping me through, and then we apply the load. And we're doing the remote force in the same way as Barry did, and we're saying that it's offset and it's just under a ton. And then I run the simulation, running it on the cloud, and we view the results. Okay.
A lot more green. I'll take that.
So I'm relatively confident that what I've done here is an improvement. So I'm going to go back to Barry now and say, right, I've done my bit. Do you want to have another look at this? And so you can see that we very quickly, we're iterating designs. We're bouncing off each other, and we're able to see what influence what we've just done has had on the design itself. So this is back to you, isn't it, Barry?
Yeah. Yeah.
Okay.
So I take your geometry that's been modified and get that information. So it's, again, it's on the platform. It's now shared. I can look at that, see what you've done, make sure it's all where we need it to be. Using the go through those steps to make sure everything's where it needs to be. I'm happy with that. Look at the plots. I can see that. Yeah. So
yeah,
if you think of years ago, Andy, doing these changes, you could make, based upon you put those parameters in there. Years ago, I used to make modifications to SOLIDWORKS from an Excel spreadsheet, but this is now uploaded to the cloud, and I can drive this from here. So I can directly affect your model without even having to be an engineer to understand, what you've done to the job, how you created the geometry. I can run that from here, change it, keep running that as many iterations as I need to. Yeah.
Yeah. So you could do a full study, couldn't you? Do some experiments to see what would work.
So you've taken that, put a lot more intelligence into that I can use based upon almost like parametric bridging. Yeah.
Yeah.
I'm going to update the geometry on there. So I've made a change. I need that to then run through that and update the physics on there. Yeah. Can see the results that they've applied as they need to be. Yeah, so I can see the report. That's now, it's significantly better from where it needs to be. Look at this von Mises stress on here. I can see it's now more stiffer. That's a term I never use.
Bad English, sorry.
Yeah. So again, I'm happy with that you've made the mods. I'm happy that I've run my tests. I can now approve this on the cloud and put in within the platform to say that, yeah, it's good to go. We can start manufacture.
So, and that's another massive thing that we're getting with the platform, isn't it? We're getting this change process that's built into the platform rather than just save as final version 2. We're getting that control, and we can set it so it's been approved by whoever.
Yeah, and you can see who done what, when, and by. Yeah.
So you've rerun your tests. So
yeah,
we're looking for a 7 for the fatigue line, and we've achieved 7. We don't want to over design it. So a 7 is what we were asked to meet, and we've met it. If we get to an 8 or a 9, then we've over designed it. So this is exactly what we're trying to do. We're trying to get to this 7 sooner. We're after a maximum stress of less than 250 megapascals. And we're getting at 225. So,
yeah.
So again, we've achieved our target. And it's been a really quick process of myself and Barry working on the same data to be able to get to this as a result.
Yeah. So like I say, I suppose one of the key things here, when you look at the ModSim stuff, you know, we can run the simulations on the designs as you go, create the studies as you go. If you remember Andy's analogy, is testing the taste test before it goes to the pass allows us to accelerate the innovations. We all know what it's like, you know, when marketing say, you know, can I have this? Can I have? But the key thing there is, yes, you can deliver that, going to improve the quality and make sure that, you know, the kit that we design, particularly if you look at this machine, that needs to be safe first time on site. We can't afford to have people, well, being killed for the worst part of it all. So we now know that that's going to be fit for function, ready to go, and comfortable with pushing the button on that one.
Yeah, and if you made that in Peru, but it's being used, I don't know, in Africa, it's a long way if you have to do a product recall, isn't it? So yeah, and then from a business point of view, the benefits that we're bringing with the ModSim and the 3D experience platform, it just, you can see how that could thrive in an environment to help innovate and get things to market faster. We're reducing the IT costs. You don't need to be worrying about having a huge simulation machine sat under a desk. You're reducing the warranty costs of recalls. With, like I just mentioned, if this machine goes off to another country, you don't want to be having to fly somebody out there to fix it. You want to be knowing that these machines,
the toolbox in the plane,
and you want to be the brand that everybody sees as the market leader. And by implementing ModSim and implementing simulation and the whole collaborative platform, that comes with it. It's just that huge step forward of making informed decisions and data-driven decisions to make sure that your product is the one that other people go to. And it might be something as simple as, if we reduce the weight of this machine by 5%, does that mean that it doesn't mean it uses as much fuel as our competitors? So we can start talking about a unique feature that means that it uses less fuel, therefore it's cheaper to run, but it's also as performant, and it doesn't wear out as quick. There's a whole host of things that we can expand on by engaging with the ModSim. And yeah, like Barry says, it's just taste little, taste often.